Before I start, I want to thank the organizers for inviting me over to give a talk. Although I'm not really a leader, and although I'm sort of not young anymore, but it's still good, to attend this meeting. It's a very nice meeting. And so I will mostly talk about something related to the nonlinear Hall effect. Inti already gave a very nice theory part of that, and I will mostly focus on the experimental part. And hopefully I also discuss it with a slightly different language. So the motivation for the work is actually to examine the conditions that, under what condition a Hall effect can actually exist. It's very well known that, ordinary Hall effect exists in non-magnetic materials under finite magnetic field, or the anomalous Hall effect, can exist under a zero magnetic field, but in magnetic materials. And and it may be, you may already know the conditions for, under what conditions the Hall effect can exist. That the Hall response should vanish for non-magnetic material, plus that is under zero magnetic field, and plus its equilibrium condition. And what I'm going to talk about today is actually we are trying to break the third condition, is drive it out of equilibrium. That actually a Hall effect can actually exist in a non-magnetic material in a zero magnetic field. So in a equilibrium condition, even though the material can be non-central symmetric and possess a Berry curvature, there's zero Berry flux when you integrate the Berry curvature over the occupied states with the equilibrium distribution function. And so what that means is actually that there should be no Hall response, and it's under zero magnetic field, and that should be the case. And it's actually guaranteed by something called an on-cycle reciprocity relation. But if you can somehow drive it out of equilibrium, that the integration now of the Berry curvature over the occupied states with a non-equilibrium distribution function, that can be non-zero, and actually that can give rise to a Hall response to the system, even under zero magnetic field for a non-magnetic material. And one of the example is actually one work from our previous work, is to actually shine light, circularly polarized light, onto a monolayer of molysulfide, which actually the circularly polarized light only couples electron hole pairs to a particular value. In this case, it will be the K value under left-handed light, for example, which will produce a non-equilibrium distribution. In this case, will be more electrons on the left, on the K value than the K prime value, and then you can actually induce a Hall response in the system. You can think of it as basically a photo-induced anomalous Hall effect in this case. Another example is the example that Inti already discussed about the nonlinear Hall effect. Or we can think of it basically like a current-induced anomalous Hall effect. That the way that it drives out of equilibrium is actually to pass a current in the system, which shifts the Fermi surface a little bit like this by the amount of momentum. P0 here is equal to basically the electric field times the scattering time, or the momentum relaxation time. And the Joule current breaks time reversal symmetry and gives rise to a non-equilibrium distribution. And as a result, you can actually recalculate the Berry curvature, integrate over with this part is the first order correction to the non-equilibrium distribution function, and that turns out to be non-zero for some materials. Okay. And Inti actually introduced this term here to be the Berry curvature dipole, which is actually it's indeed like it's like a dipole of Berry curvature distribution in the momentum space because of the shifted Fermi surface. And another way to really think about it is actually that, as I mentioned, it can be thought of as a current-induced anomalous Hall effect. And one way to think about it is really that there's a current that drives an outer plane magnetization in the system. That is a Hall response to this outer plane magnetic moment to the system that gives rise to a Hall response. So that's why it's nonlinear to the current, to the driving current. And you may have a question like, does this actually occur in all type of non-central symmetric material? And it turns out that this question is related to a paper by Edelstein in the 1990s talking about under what situation that a current can drive a magnetization in the system. It turns out that what you need is actually a polar metallic system with a polar axis, that a current passed perpendicular to the polar axis can generate an outer plane magnetization. All right, so this talk I will talk about two things. One thing is about the measurement of a current-induced magnetic moment in a polar two-dimensional semiconductor, and the other one is about the second part of the talk. I will talk about the effect on the transport due to this current-induced moment in the system, which is the nonlinear Hall effect. Just a few words about monolayer semiconductors, for in case that the audience is not very familiar with. The system we are looking at is moly disulfide, which consists a monolayer of material with 3 layers of atoms with the moly sandwiched between 2 layers of sulfur. And if you look top down, it looks like graphene with a honeycomb lattice structure, and the brilliant zone is like this, and the bands of interest are near the K and K prime point of the brilliant zone, just like graphene. And a simplified band structure is something like this. Basically, it's like a massive Dirac fermion that with the energy gap open at the K and the K prime point because broken immersion symmetry in the system, that the A and B lattice sites are occupied by different atoms. And it's a semiconductor, so in the pristine case would be that the Fermi energy is located inside the energy gap of the system. All right, so what's somewhat interesting in this material is actually that there's a very contrasting Berry curvature that you can think of it. Once you open the gap in graphene, you release the Berry curvature. In this case, that for example, if we consider the conduction band, there will be positive Berry curvature at the K point, at the K prime point, and negative Berry curvature at the K point. And this very contrasting Berry curvature actually allows you to couple light with a particular handedness to a particular value. For example, left-handed to the K and right-handed light to the K prime value. Okay? And that's basically a short summary of about this material. And a natural question to ask is actually, is it possible to use a current to induce an out-of-plane magnetic moment in this system? And in particular, once you pass a current in the drive a current in the material, you tilt the Fermi surface, and on this side it has positive Berry curvature, on this side it has negative Berry curvature. Can we get a net Berry flux in the system and produce a net orbital moment due to this current? So in particular, is it possible to actually this should be an integration over the non-equilibrium distribution function. Is it non-zero or zero? And turns out that actually the answer is that it's zero for this type of material. One can think in terms of, one can think for the current-induced magnetic moment as a magnetoelectric effect. In this case, it's actually called a kinematic magnetoelectric effect, introduced by Levitov. And the moment that is created by the driving electric field with the coefficient alpha ij, which is known as the magnetoelectric coefficient. And for the kinematic effect, a current is involved, so that the magnetoelectric coefficient is proportional to the tau, the momentum relaxation time system. And it's also well known that the necessary conditions for a non-zero, magnetoelectric coefficient is actually to break this two symmetry, to break the inversion symmetry, which already is satisfied in a monolayer of moly sulfide. And the second condition to really break the time reversal symmetry, and in this case the time reversal is broken by the current, by the Joule current. That's why actually the magnetoelectric coefficient is proportional to the momentum relaxation time. Then it seems that a monolayer moly sulfide actually under current biasing condition that we should be able to get a finite kinematic magnetoelectric coefficient, but actually that does not really generate an out-of-plane magnetic moment or an nonlinear Hall effect in the system. The reason is just that actually you can think of it, there are 3 polar axes in the crystal, but the 3-fold rotation symmetry actually just completely cancel. There's no net polar axis in the crystal because of the 3-fold rotation. Or if you look up the the magnetoelectric tensor table from some book, that this actually add together should be 0 because of the 3-fold rotation symmetry. On the other hand, if we can apply strain to the material, that actually lowers the 3-fold rotation symmetry, and actually that creates a net polar axis in the system, which I actually denoted to be pointing in that direction. And in that case, actually, under the strain, a new element is actually now allowed that the in-plane electric field and in-plane current can now generate an out-of-plane moment in the system. And that's something that we actually want to study whether this is the case. And to do that, what we do is actually we want to make a transistor device out of this semiconductor. When you have a semiconductor, you make a transistor device. That's the normal thing that you would do for people playing the semiconductor like me. So what we do is actually that we try to we first put down the electrodes on the silicon substrates with a layer of silicon oxide that actually can be used as gate. and we just put down the whole bar device, whole bar electrodes, for example, and we just strain the material, and then we transfer. We just stamp onto the electrodes we have. Okay, and in order to know which direction we are actually straining the material, we perform a second harmonics generation experiment, which can actually nicely tell you that the six-fold pattern here is really related to the three-fold rotation symmetry of the crystal. Then you will know that actually if you apply strain along this direction, it's going to be along some high symmetry crystal axis of the system. And to really know that we actually are applying strain, at the same time we monitor the photoluminescence peak from the material. Typically a strain would just lower the band gap or the energy gap of the material, and we will see a redshift actually that would be the redshift in the energy of the emission. So we actually would know how much strain we are putting onto the system by just monitoring in real time the amount of strain we apply to the system, and we also know the direction of strain we actually put on the system. And then we just stamp on it, and some of the devices can keep the strain, but some other devices don't keep the strain. And the strain is also not continuously tunable in this situation. Okay, so this is, for example, a particular device that with two electrodes like this, and the experiment we do is actually in terms of probing the magnetic moment induced by the current is basically to do a magnetooptical Kerr effect microscopy. We drive a current in the device and we shine nearly polarized light. And if there's a current-induced magnetization in the system, then there will be a corresponding rotation in the polarization of the system. And we just detect that small rotation in the polarization of the light. Okay. And then there's also a backgate that actually connects to the sample that can change the Fermi energy of the material. And so this is the case actually for a strain-free device that if you don't apply any strain to the device, you would actually still see signal. This is the co-rotation map as a function of xy coordinate, and this you actually will see signal on the two edges of the sample, and they have opposite sign. And the reason for that is actually just a very Hall effect in the system, because actually you have a very dependent barrier curvature with positive barrier curvature at K point and negative barrier curvature at the K prime point. So if you drive a current, the K and the K prime electron will develop anomalous Hall velocity. Anomalous velocity that actually accumulates a net magnetization only on the edges of the sample. That's actually purely due to the very Hall effect. For a strain-free device, you only see a signal on the edges. But for a strained sample, in this case, we apply strain along the zigzag direction for about 0.5%, in this case, the strain. Then actually the result is completely different. This is for the situation that the current is passing to the upward direction, and you actually see that the Kerr rotation signal now just brightens up everywhere in the sample. It's more consistent with the current-induced magnetic moment. Now you actually see magnetic moment generated everywhere in the sample. If you reverse the current direction, you just see that the sign of the magnetic moment just flipped. I just expected that. That's expected the case. So this is just to verify that since we strain the material, we want to exclude the possibility of birefringence in the crystal, because now it actually becomes slightly birefringent. So what we do here is we probe the Kerr rotation angle as a function of the incident polarization on the sample, and basically the signal is independent of the incident polarization angle. It's consistent with a magnetic moment rather than a birefringence, because if it's a birefringence signal, then there should be a signal that that's dependent on which direction of the polarization with respect to the applied strain. All right, so and also to prove that this is really driven by current, so on the left side we plot the conductivity of the sample as a function of gate voltage. It's an N-type transistor, so that it gets turned on for apply a positive gate voltage, a different temperature, so it turns on at a positive gate voltage, and you can actually see that the Kerr rotation signal in the bulk of the sample also turns on, basically following the shape of the current. So it really proves that it's basically the magnetic moment is really generated by the current, by the driving current of the sample. And we also have done bias dependence and etc., really to show that it's really induced by the current. Okay, so this is what we think for the microscopic picture. What's happening for this current-induced magnetic moment in the system is that for pristine, meaning unstrained sample, strain-free sample, under the equilibrium condition, you guarantee to have zero barrier flux. And without strain, you apply a bias, drive a current, you get a non-equilibrium distribution, but you can basically see that this side has a positive Berry curvature, this has a negative Berry curvature. Even with the non-equilibrium distribution function, when you integrate over, you still actually get a zero Berry flux in the system. And what strain does is really to shift the band minimum or the band maximum a little bit away from the K and K prime point of the Brillouin zone. And if you at the same time drive a current, in this case, that now the tilted Fermi surface, when you integrate over the Berry curvature, because of this shift in the band minimum or the maximum, then you actually will get a non-zero Berry flux or a magnetic moment in the system. And one can calculate that this is actually proportional to the current cross product with the direction of the polar axis. So it's a very simple rule that just the cross product of the current with the polar axis that would generate that moment. It's a bit like spin-orbit interaction, but it's a unbalanced spin-orbit interaction between an equilibrium distribution function. All right, so finally, we want to test this a cross-product relation. And this is the kind of device we make. We just make a disk device that can pass radial current just at all different directions. And this particular sample we strain along the armchair axis. And you can see that this is the polar axis, and this is along the strain direction. And you only see Kerr rotation signal on the two sides of it. You don't really see Kerr rotation signal along the axis. And the Kerr rotation signal actually has opposite sign. It agrees quite well with the simulation based on this straight cross relation. And we can also do the same thing of stretching the sample along the zigzag axis. And basically, you just get a very, very similar pattern of that. So it really proves that this is something that is related to, it follows also this expected vector relation. Okay, so that is really the first part that actually that we can detect a current-induced magnetic moment using optics in this system, and you may just wonder actually then we should actually be able to observe the nonlinear Hall effect also in a strained monolayer molysulfide. But turns out that in that system it's actually difficult because first of all the strain is tiny and we can apply as tiny, so it does not really create a very strong polar axis in the material. And the second is just that it's much more difficult to make contacts and 4-point reliable measurements on a semiconductor. So actually we're switching our effort in terms of probing the nonlinear Hall effect. We're switching the effort to on the TD structure of tungsten telluride. So tungsten telluride in the monolayer case, it's central symmetric. So it's in this audience, that means actually it's more boring, and so it's central symmetric. And it's probably not that boring because it's a topological insulator. I just take that back. And so in the field layer case, actually, but you can already see that this is a distorted honeycomb lattice structure. No, it's not honey. Yeah, it's a distorted structure that the tungsten atoms actually they are dimerized along a particular direction. And but if you actually stack a few layers on top of each other, the stacking plus this dimerization of the tungsten atom actually breaks the immersion symmetry and introduce a polar axis along the mirror line of the crystal. So it's a polar semi-metal, in this case, that with a polar axis along the mirror line, so it would be an ideal system to probe the nonlinear Hall effect. And our group and also Pablo's group made very similar devices. We focus more on the semi-metallic region, and Pablo is focusing more on the more close to the insulating case for a bilayer sample. And this is a Hall bar device. We try to align the A-axis, parallel to the driving current, so that the mirror line is actually, or the polar axis is perpendicular to the driving current. And this is the linear response that we actually get this is the longitudinal voltage, nicely scales with the driving current, and we get very little XY mixing, very little Hall transverse voltage in this device because of the good alignment of the crystal axis and relatively good sample geometry of this material. And you can look at the temperature-dependent resistivity. It's basically like a metal behavior. And you can also do a magnetotransport studies that actually can see the usual large magnetoresistance, non-saturated magnetoresistance, as well as the Hall response. From this data, we can actually extract the electron hole density as well as the mobility is about 1,000 to 2,000 centimeters squared per volt per second. Okay. So the device is reasonable, it's okay. And then we switch to look at the nonlinear Hall response. And this, I showed that the measured Hall voltage at the second harmonic frequency as a function of the driving voltage squared. And you can see that basically in this connection geometry, that you just see a very nice linear relation. Basically shows that it's really a nonlinear effect. And if you rotate your coordinate system, 180 degrees, then the sign of the Hall response actually switch sign. That's really just reflecting the fact that your current-induced magnetic moment is just flipping sign when you reverse the direction of the current. And not only we can actually see the second harmonic response, we can also see the rectification response, the DC response. You just drive it with a AC voltage, you can actually see a DC Hall voltage that is developed. Also scales quite nicely with the square of the driving voltage. Okay. And actually, I also would like to point out that it's a little crazy to see a big nonlinear response in a system with pure CW driving, because the usual system that you would expect to see big nonlinear response or detectable nonlinear response would be using pulse lasers that you shrink the energy into a really short pulse to increase the electric field of the driving. But this is purely CW driving and not a very large electric field that is applied to the sample. So it's probably reflecting that pretty big very curvature in the system. And also, we check the angle-dependent transport by making this a device with 16 different electrodes, and we just rotate our coordinate frame on the sample and just keep measuring the Hall response of the system. And this is the linear transport coefficient, and you just see that the resistance is minimized at the A-axis and maximized at the B-axis, which is consistent because the crystal has a particular mirror line is actually birefringent, so that the resistance is actually dependent on which direction you're measuring at. And so it's consistent with the crystal symmetry, and also the same for the nonlinear Hall response. This is the nonlinear Hall susceptibility, which is the nonlinear Hall voltage divided by the voltage square, which is actually the slope in this graph here. That's the nonlinear Hall susceptibility. As a function of the angle in this system, you basically can see zero response when the current passes through the mirror line, but you see maximum response when the current is perpendicular to the mirror line of the system. And the two sides has an opposite response, just reflecting the fact that the current-induced moment is just switching sign by just switching the direction of the current. Okay, and so the last question we want to answer is that whether it's an intrinsic response or an extrinsic response for the system. And what is an intrinsic response is mainly the response that Inti talked about that is driven by the Berry curvature dipole. So we define a nonlinear Hall susceptibility, which is the second harmonic or the rectification transverse electric field divided by the longitudinal electric field squared. And if it's an intrinsic response, it's just proportional to the integral of the Berry curvature over the non-equilibrium distribution function. That it turns out that this quantity is independent of sigma. It's independent of the longitudinal conductivity of the sample. And this is also just like the anomalous Hall effect, because this is really just like anomalous Hall effect, that this should also be the extrinsic response. The extrinsic response is usually just separated into two kinds. One is a skew scattering, that the spin-up, spin-down electrons, in this case. The spin-up, spin-down electrons will just go off at a different angle. And this side jump response is basically a pure displacement of the center of coordinates of the spin-up, spin-down electrons. And for the first contribution, it's expected to be proportional to sigma squared, okay, if you vary sigma by varying temperature. Or and the second response side jump is just like the intrinsic response is independent of sigma. And so you would expect that basically the nonlinear Hall susceptibility to be proportional to sigma square plus a intercept term that it contains both contribution of the intrinsic and the side jump. And so we just vary the temperature of the system, and this is the temperature-dependent conductivity of the sample, the longitudinal conductivity, and this is the temperature-dependent nonlinear Hall susceptibility. And you can scale them. Just this plot is taken from this data. The nonlinear Hall susceptibility scales with the square of the sigma, which actually a pretty good linear relationship is seen as expected from this relation. And you can extract now the intercept, the y-intercept here, which is actually related more to the intrinsic response of the system. And then you can put an estimate of the Berry curvature, which roughly, I just put a rough estimate, which is this intercept times the Fermi energy of the system that will give you a 50 picometer Berry curvature dipole, which is on par, with the calculation of the system. And I think my time is basically running up. So I just want to very quickly highlight, recently we tried to make gate-dependent devices which can change the electron hole density as well as basically mainly changing the electron hole density. And we performed the same exercise of scaling of the nonlinear Hall susceptibility with the conductivity at different gate voltage. So at each gate voltage, we just do a more careful temperature-dependent study. And then we extract basically the y-intercept as a function of doping density, and around the charge neutrality point, compensation point, that actually there's a switch sign in the, looks like a switch sign in the intrinsic response, which is more related to Berry curvature dipole. Seems to be sort of consistent with theoretical calculation that there is indeed a switch sign in the Berry curvature dipole near the charge neutrality point. And besides actually changing doping density, because it's a gated device, now we can also actually apply electric field onto the system. And it's reported that this system is actually ferroelectric, which the polar axis could potentially be switched by a pure electric field. And indeed, we can see the ferroelectric response in the sigma XX, the longitudinal conductivity. But at the same time, the nonlinear Hall susceptibility can also change sign by this ferroelectric switching, so which shows that potentially this polar axis of the Berry curvature dipole actually can be switched sign with this applied electric field. And with that, I just want to thank the people involved in this work. And the current-induced magnetic moment is mainly driven by our former postdoc, Juan Lee. And the nonlinear Hall effect is mainly driven by our student, Kai-Fei Kang. And I share a group with Jishan at Cornell, and boron nitride supported by the Japanese group. And with that, I thank you for your attention.
Thank you. Questions?
Did you try MOTE2? It has a
yeah, did not try, but it seems that you should also expect a nonlinear Hall response in the system. It's actually interesting to try. And in MOTE2, it seems that immersion symmetry is only broken in the even layer number, so that by just changing the different layer number, that you probably just get zero and non-zero nonlinear Hall response.
The talk also has a structural transition around to symmetry pellet, right? Which changes crystal structure from.
Yeah. Then you probably also will see a big change in the nonlinear Hall response if you have a change in the crystal structure.
Here, actually, what do they mean by ferroelectric? It's still a semi-metal, right? I don't think.
Yeah, actually, so it's like whether a ferroelectricity can exist in a metal or a semi-metallic system. And basically, for bulk material, that cannot exist because it's just the polarization is screened out by the free carriers. But in this case, actually, you can make the thickness of the crystal to be much thinner than the skin depth.
So then you can even measure, you can even detect polarization.
Yeah, you can detect polarization. Yeah, and that's actually that's sort of the David Cobden's experiment, that he's using a piece of graphene nearby the tungsten telluride and applying the electric field, and that polarization will change the graphene doping level a little bit, and he could actually use the graphene to remotely read out the change in the polarization.
So he's doing some surface charge measurement.
Yeah. But you can also measure it by really measuring capacitance, for example. And I don't know anybody did that, but that should be a strong capacitance signal as well, this transition.
Yeah. Oh, I was having a question about that. Here, what you measure is like this is a 3-layer or
yeah,
thickness.
This is he only can estimate it's about 4 to 5 layer.
I see.
Tungsten telluride. There are some theoretical proposal of like actually whether the in-plane polar axis can switch would depend on whether it's an odd layer number or even layer number, and we I'm not entirely sure whether it's an even or odd layer number in this case.
I see. Here, this polarization switch is the z-axis.
Yeah, this is the z-axis, but I think the idea is that if it's an odd layer number, the ferroelectricity is related to the displacement of the ions in the crystal. And because of that switch, there's also a small in-plane displacement. That can also change the in-plane polar axis as well.
Yeah. Okay, do we have more question? If not, let's thank Fine and also Inti